Hello everyone, my name is Anis El-Gibli. I'm a postdoctoral researcher at the Center of Wireless Communications, University of Oulu in Finland. Today I will be presenting our communication efficient decentralized machine learning algorithm named Quantized Group ADMM. With Internet of Things paradigm, a huge amount of data is generated everywhere and every second. Here are some examples of IoT applications and use cases. We have smart cities, smart healthcare, smart farms, connected vehicles, self-driving drones, and smart industry. With the large number of IoT devices and the huge data they generate, machine learning computations need to move to the edge. And to show the necessity of that, let's compare distributed learning with centralized learning. As shown in the figure to the left, in centralized learning, every node needs to send its raw data to the central server in both training and inferring phases, which creates high communication cost and and high latency issues. Moreover, this approach creates a privacy issue since data leaves its origin. In contrast to that, in distributed learning, as shown in the figure to the right, every node uses a local machine learning model and it needs to communicate with the parameter server only in the training phase to update its local model. And it needs to exchange few parameters, for example, the model vector or the gradient vector or the model output. And that leads to significantly less communication cost and lower latency. It also preserves the privacy since no raw data exchange is happening. In the previous slide, I described the distributed machine learning with a tree topology. However, in general, distributed machine learning is divided into two settings: centralized, which was described in the previous slide, and decentralized. In decentralized topology, as shown in the figure to the right, every worker needs to communicate with few neighbors. Therefore, this could be useful in the absence of parameter server or when the link to the parameter server is costly to use. As described in the second slide, in distributed machine learning, every worker exchanges minimum number of variables with the parameter server per training iteration. Those variables could be the gradient vector, the model parameter vector, or the model output. However, to further enhance the communication efficiency of distributed machine learning, several approaches were proposed in the literature. One way to further enhance the communication efficiency is to introduce time sparsity, so each worker doesn't need to transmit at every iteration, so the number of workers who can transmit at every iteration of the training algorithm is minimized. To minimize the payload size per channel use, quantization of the transmitted data was also considered. In our prior work, Group ADMM, we considered spatial sparsity, where we decentralized the topology and minimized the number of neighbors that each worker needs to communicate with. We also show fast convergence of this algorithm. In this paper, we extend Q-GADMM algorithm and we add model quantization to minimize the payload size per channel use. We utilize stochastic quantization to amplifies the quantization error, and we also decrease the quantization step size per iteration. And with those considerations, we show that quantized Q-GADMM inherits the same convergence guarantees of Q-GADMM for convex loss functions. Before I jump into describing Q-GADMM and its quantized version, I would like to briefly describe standard ADMM algorithm. ADMM stands for alternating direction method of multipliers. It solves this constraint optimization problem where the objective function is sum of convex separable functions and capital theta is a global model or a global variable. The ADMM formulates the augmented Lagrangian, which has one additive term compared to the standard Lagrangian that is used in the in dual decomposition. And in fact, the additive term is this quadratic term where rho is a positive number. At iteration k+1, the primal and dual variables are updated as follows. First, all the workers in parallel, every one of them update its own model using the kth version of the global model and the kth version of the dual variable. And then all workers transmit their updated models to the parameter server. The parameter server will use the updated models of all workers to update the global model, and then it will broadcast the global model to all workers. Then the dual variables can be updated at the worker side as well as the parameter server. Now we describe our decentralized implementation of ADMM, group ADMM. We change one thing in the constraint, so we rewrite the constraint in this way. We say theta n is equal to theta n plus 1. So every worker has two joint constraints, one with the previous worker and one with the next worker, except of course the first and the last workers. With that, group ADMM works as follows. We divide the groups, workers into two groups, head group and tail group. All odd workers belong to the head group, and all even workers belong to the tail group. Every worker in the head group is communicating with two workers from the tail group. And the same thing applies for the tail for the workers in the tail group. So at iteration k plus 1, first thing, all workers in the head group update their models in parallel, since they do not have any joint constraints. So they all update their models in parallel. After that, every worker in the head group broadcasts its updated model to its two neighbors from the tail group. Then every worker in the tail group will also update its model, and then it will share its model with its left and right neighbors from the head group. After the primal variables or the models of the workers are updated, the dual variables updated, and each worker can update the dual variables locally without any need for extra communication. Here are the mathematical steps. This is the augmented Lagrangian. As I just mentioned, the primal variables of the head groups are updated first at iteration k plus 1. And then after that, the tail workers update their models. After the primal variables are updated, the dual variables are updated locally at every worker. Now I describe the convergence and the optimality conditions of GADMM for convex loss functions. I'm not going to go into the details, but I will highlight the main steps. The necessary and sufficient optimality conditions are the primal feasibility and the dual feasibility. The primal feasibility states that at the convergence and the optimal point, the models of all workers are equal. The dual feasibility states that theta star and lambda star are the optimal solution of the Lagrangian function. At iteration k plus 1, we define two terms. The first term is the primary residual, which is equal to the model of the nth worker minus the model of its right neighbor, and this will go to 0 at the convergence point. And the dual residual, which is defined for the head workers, and it's a function of the difference between the current and the previous model of the left and right neighbors of worker n. This term will appear in the Lagrangian function at every iteration, and we'll show eventually this term will also go to 0. Now I'm ready to introduce our first lemma. This lemma imposes upper and lower bounds on the optimality gap at iteration k plus 1, and those bounds are function of the primal residual and the dual residual. Therefore, if we show that the primal residual goes to 0 and the dual residual goes to 0, then these upper and lower bounds will meet, and they will exactly meet at the optimal point. And in fact, that's what we proved in the main theorem. So we show as GADMM iterate, as k goes to infinity, the primary residual goes to 0 and the dual residual goes to 0. Therefore, the optimality gap goes to 0, and the objective value converges to the optimal value. Now I describe quantized GADMM. We follow the same steps of GADMM, except that each worker shares a quantized version of its model with the neighboring workers. As shown in the figure, the stochastic quantizer at iteration k is centered by the previous value of the model, and it also defined by a few other parameters. The first parameter is the quantization range, which is defined by the maximum difference between the current and the previous model. The quantization step size, which is equal to the range over the number of quantization levels, and the probability of rounding every element, the probability of rounding up every element in the quantized vector bi. So we round every element up with the probability bi and down with the probability 1 minus bi. To maintain unbiased error with zero mean, BI should satisfy this equation. Basically, BI should drive the expected value of the error to zero. Moreover, to guarantee convergence to the optimal solution as k goes to infinity, the quantization step size should be decreasing with k. And in order to satisfy that, the quantized resolution or the number of bits to encode every quantization level should satisfy this inequality. And in fact, in practically, we found like RNK is decreasing every iteration, so we don't really need to change the quantizer resolution every iteration. After quantizing the model difference, worker N transmits the scalar values Rnk and Bnk, and also the quantized vector Qnk, which are transmitted using Bnk times D bits, where D is the vector length plus B are bits for the quantization range, and BB bits for the quantizer resolution. And that could be significantly less than 32 times D bits required in full precision communication as D grows large. At the neighboring workers, the Kate model of worker N can be the quantized version of the Kate model of worker N can be retrieved using this equation, using the previously quantized model plus the current quantization value of the model difference. The steps of updating the dual and primal variables very similar to GADMM, except that every worker is using a quantized version of its neighboring workers. And at the equation of updating the dual variables, we use the quantized versions of the models. The convergence analysis follow similar steps to GADMM case. So we have primal and dual feasibility conditions. We have the same definition of a primal residual. For the dual residual, we use the quantized versions of the models. This dual residual will appear at the augmented Lagrangian function at every iteration, and eventually we will go to zero as far as the quantization step size is decreasing. Now we are ready to introduce the first lemma. The first lemma imposes upper and lower bounds on the expected value of the optimality gap at iteration k plus 1. And these bounds are function of the primary residual, the dual residual, and the quantization error. We also have another lemma. This lemma basically introduces this inequality. This inequality says the expected value of the difference between the optimality gap at iteration k and k plus 1 is upper bounded by this value. In fact, if k plus 1 is one step toward the optimal solution, then this expected value should be greater than or equal to 0. So we see this is a positive term, and HV is defined here as a positive term, but this one may not be positive. However, delta NK is decreasing over iterations, and eventually this will go to 0, and that brings us to the main theorem, which states that as far as the quantization step size is decreasing and we are utilizing stochastic quantizer, the primal and the dual, as k goes to infinity, the primal and the dual residuals will converge to 0 with a probability 1, and the optimality gap will converge to 0 also with a probability 1. So the objective value will converge to the optimal value. We now describe the simulation setup and simulation results. We conducted an experiment using linear regression, and we compared it with GADMM, gradient descent, and a quantized version of gradient descent using a real data set. Now I describe the simulation results. As we can see from subplots A and B, both quantized GADMM and GADMM require the same number of iterations and the same number of total communication runs to achieve the objective error of 10 to the minus 5, and they both significantly outperform the considered baselines. However, as we can see from subplot C, when we consider the communication overhead per channel use, the actual transmitted bits, we can see like a quantized GADMM with 2-bit quantization resolution can achieve the objective error of 10 to the minus 5 with significantly less number of transmitted bits. It's around 7 times less. Now I come to the conclusion. Compared to the original GADMM, quantized GADMM enjoys the same conversion speed, but at significantly lower communication overhead. Numerical results show that quantized GADMM outperforms all the considered baselines. For the future work, we aim to extend quantized GADMM to arbitrary and time varying topology, and also to non-convex and stochastic problems such as classifications using deep neural networks. To know more about our GADMM work, please check these two papers. For questions, please don't hesitate to email me. This is my email. And finally, I would like to thank you for watching my presentation. Thank you.